In this problem, we're looking at the number of cases of salmonella in thousands as a function of the percentage of corn crops that are genetically engineered with either insecticides or herbicides P. First thing we'll do is we'll identify our outputs and inputs. We know that this relationship as an output is going to be the cases of salmonella. So I'll abbreviate that and I'll write thousands, because that's in thousands. And then our input is, well, we're trying to figure out cases of salmonella based on how many or what percentage of our crops in the United States are genetically modified. And that's what P represents. So percentage of genetically modified or genetically engineered crops. Okay, so the relationship is given to us more mathematically via this exponential function, which, if you recall from earlier classes, increases at a faster and faster rate. That's what we know about it. And here we have our output, cases of salmonella. Here we have the percentage of GM crops. And of course, we do have a cap on this thing. We don't really want to study this thing beyond 100%, but we can definitely say that it's going to increase based on this model. That is, the cases will increase as percentage of GM crops goes up. In part A, we just simply want to know the number of cases when 20% of crops are genetically modified. Well, that gives us the percentage. We want to figure out the number of cases. So what we'll do is we'll just replace P with the correct value, which is 20. And we could do this one of a couple of different ways. We'll just do it longhand first, 39.1. To get E, you hit second ln. 0.003 times 20 and hit enter, and it predicts about 41.5 thousand cases. Perfect. So another way we could do this is so that we don't have to always type in the full equation and have this big mess on our screen, is to enter this into our y equals screen. So we'll type in 39.1 second ln, and we'll type in 0.003, but you don't want to hit in times 20 because you want to be able to have x change as you want it to. So what we'll do is we'll just do 0.003x. That's of course representative of our P, but there is no P button in the calculator. And so now when we exit, what we can do is actually access this equation and say, hey, you know what? I want the outputs of y1 based on different values of x that I give you. So the first thing we'll do is we'll pull the y1 symbol in. We'll hit vars, yvars, function, y1. And just like function notation, this is the output as a function of an input, which in this case, in letter A, is an input of 20. So give me the output of the function 39.1 e to the 0.003x when the input is 20. It tells us that's 41.5, which is very consistent with what we found up above. Okay, so that of course means that there are 41.5 thousand cases, which is 41,500. In letter B, we want to find the average rate of change in salmonella per percent increase in genetically modified corn crops between 10 and 80%. Then explain. Okay, so we want change in output over change in input. We identified output, we identified input. You probably want to think about how the cases go up or down based on what happens to the percentage. You probably don't want to study the percentage of GM crops based on what's happening to cases. It's just like dollars per hour versus hours per dollar. Hours per dollar is probably not something that you really care too much about. Maybe you do. And so we'll have cases per percent. And we know that the percentage changes from 10 to 80. So changes from 10 to 80. But now the problem is I need to go back into this relationship and figure out what this model predicts given these two percentages. So a simple way to do that is just to type the y1 of, and then 80, the y1 of the 10. But what I'm just going to do is hit second enter, so I don't have to go and grab the y1 from vars, yvars function, and I can just kind of back scroll and change the 2 to an 8. And that's about 49.7 minus second enter, and now we'll just change that value to a 10. And it's 40.3. And now if I find the difference, I'm going to put the numerator in parentheses. Minus 40.3 divided by 80 minus 10. Works out great. We get 0.13 thousand cases per 1% increase in GM crops. So there's 0.13 thousand more cases, we should say, per every 1% increase in GM crops. Now, a simpler way to do this is rather than to have to find these outputs, write them down, and then figure out this rate of change, notice that 49.7 was the output from y1 of 80. 40.3 was the output of y1 of 10. So why not, in the numerator, just enter vars, y vars, function, y1, parenthesis 80, because that's exactly what 49.7 comes from, minus vars, y vars, y1 of 10, parenthesis, oops, forgot to open parenthesis. So notice I'm just saving myself a little bit of work. Try this again. And now I close the parenthesis, so there's my change in output divided by 80 minus 10. And now, in all its glory, I get a more precise answer with less rounding error. Obviously, these two are different by some rounding error, and this one gives it to me more exactly because notice that when I wrote stuff down, I rounded it off. Here, I didn't have to do that. Okay, in part C, we want to know the average rate of change in the salmonella per percent increase in GM crops between 70 and 80%. So all I have to do is hit second enter and just change my 10 to a 70. Save myself a lot of headache. As long as I know what I'm doing, I don't have to manually do everything. And now I find out that that rate of change is actually about 0.15 thousand more cases per 1% increase in GM crops. So as you're noticing here, and you probably learned about exponential functions, as time goes on, this thing moves faster and faster. It grows, but it grows faster as time moves on. So here we actually see that. Part D wants us to know, is salmonella case increasing at an increasing or decreasing rate as more crops or GM are genetically modified? Well, if this is 10 and this is 80%, and we draw a line that represents the average rate of change, and now we move that point closer so that it's 70 and 80%, notice how I'm actually more precisely determining how quickly things are moving because I'm more current with the times. In other words, my percentages are closer together. So we get a bigger and bigger slope, and as this thing moves up, it's going to kind of grow and grow and grow, and we get a larger and larger slope. So the answer is it's increasing at an increasing rate.